October 30th, 2025. For weeks, astronomers had anticipated this moment. They expected turbulence, solar heating, perhaps a brief brightening as its volatile compounds were stripped away. And then, silence. A slow fade. Just another comet. Outgassed, fragmented, forgotten. But that isn't what happened. Instead of fading, 3I Atlas intensified. Not slowly, not randomly, but with startling precision. Its coma, expected to disperse after solar heating, grew denser, more symmetrical. Its spectral profile, once vague and diffuse, snapped into definition. And from the center of that blooming haze, something emerged. Something no one expected. A pulse. 1.44 gigahertz. Weak. Consistent. Deliberate. At first it was dismissed as noise, but the timing repeated, the source aligned, and across observatories from Chile to Japan to deep space antennas in Australia, the same signal echoed again, every 32 seconds like a heartbeat in vacuum, and with it, the question that had haunted astronomers for over a year resurfaced with new urgency. What is 3I Atlas? Some say it's a comet, an interstellar relic from another star system. Others believe it's a probe, engineered to behave like one. But now, after Perihelion, that debate is no longer theoretical, because something changed, and what we're seeing now doesn't match any known natural model. The coma isn't collapsing. The trajectory isn't passive. The light profile, acceleration pulses, and electromagnetic emissions suggest a system that is not just surviving, it's functioning, in ways we can detect, in patterns we can chart, in signals we can no longer ignore. So tonight, we're breaking it down. From the strange infrared readings to the optical flicker patterns to the silence of official agencies, and the one date that now appears to tie it all together, December 19th. Because according to the latest orbital data, 3I Atlas is not just drifting, it's aligning. And the evidence we're about to show you may change the way you look at every so-called comet that came before. Before we begin, take a second to subscribe. This story is still unfolding. Drop a comment with where you're watching from and what time it is in your part of the world, because by the end of tonight's breakdown, you'll understand why a growing number of researchers now believe 3I Atlas didn't just survive Perihelion, it activated. This is the 3I Atlas channel, calm, focused, and based on verified solar system telemetry. If you want to be part of this mission, hit subscribe right now. Comment Atlas below to join the Data Watch and enter our exclusive 3I Atlas hoodie giveaway. Tell us where you're watching from and the exact time where you are. October 30th, 2025. After months of anticipation, 3I Atlas reached its perihelion, its closest pass to the Sun. For astronomers, this was supposed to be the moment where the object began to fade. Perihelion is typically a peak of activity, followed by a slow decline. Ice vaporizes, solar radiation pushes dust outward, and for most comets the coma disperses as they retreat into colder space. But 3I Atlas didn't follow that script. Instead of weakening, it brightened, sharply. Spectral data from multiple observatories showed an unexpected rise in luminosity across several bands. Instead of dissipating, the coma around the nucleus thickened. Instead of cooling, the structure appeared to organize. High-resolution imaging captured jets of material that didn't seem to follow the usual solar wind dynamics. One jet, in particular, was directed toward the Sun, not away from it, an inversion of the natural behavior seen in outgassing comets. That inversion triggered alarm bells. Observers from Chile's Cerro Paranal Observatory were among the first to publish data that hinted something had shifted. The coma structure had altered geometrically, forming what appeared to be a symmetric lobe on one side consistent with localized energy output. This wasn't just solar heating. Something was distributing energy within the object. But the strangest development came not from visual data, but from the radio spectrum. Just hours after perihelion, a faint but structured signal was detected at a frequency of 1.44 gigahertz. Rhythmic, repeating, and narrowband. This wasn't random noise. The spacing between the pulses was steady enough to suggest a clock source, something synthetic or at least highly regulated. Multiple amateur and professional radio astronomers across Earth confirmed the same detection. The signal didn't last long, only a few minutes, but it was enough to reopen a debate many believed was settled. because before Perihelion, the case for 3I Atlas being a conventional interstellar comet, albeit a rare one, was strong. It had a visible coma. It was hyperbolic in trajectory. It showed some signs of outgassing. That fit the known playbook. And while some anomalies existed, such as its high carbon dioxide content and its unusually flat orbital inclination, these were framed as statistical outliers, not signs of artificiality. But Perihelion shattered that assumption. The combination of behavior, structural reorganization, symmetrical jetting, an expanding coma despite peak solar heating, and the emergence of a radio pulse forced a re-evaluation of what 3I Atlas actually is. Was this truly a natural object responding to solar heat in an unexpected way? Or were we witnessing a controlled maneuver, an activation event timed precisely for closest solar proximity? Even skeptics had to admit. The timing was hard to dismiss. If this was simply ice sublimating, why had the signal emerged only at perihelion and not during the inbound phase when solar heating was already intense? Why had the visual structure of the coma changed so drastically, with no apparent mechanical stress to force such a transition? One theory quietly making its way through academic circles proposes that perihelion served as an ignition point, not for combustion, but for a system activation, a trigger. The moment when internal mechanisms could begin operating thanks to optimal solar energy intake. If 3I Atlas were a probe, perihelion would be the logical moment to switch on, to power sensors, to transmit data, or to adjust course. Whatever the mechanism, the outcome was clear. After perihelion, the object wasn't just behaving differently, it was behaving with intention. And that's why this moment matters, because in astronomy change isn't suspicious, unless it breaks the model. And this object, in those few hours around October 30th, broke every single one. The brightening began subtly, then accelerated. In the days immediately following perihelion, observatories across the globe started reporting a steady increase in brightness from 3I Atlas. Not just in one wavelength, but across the visible spectrum. The object, instead of fading as it moved away from the sun, was growing more luminous. For seasoned cometary scientists, this was the first red flag. Typically, cometary brightness peaks slightly before or exactly at perihelion. The intense heat causes surface ice to sublimate, releasing gas and dust into the surrounding coma. This creates the glowing halo we associate with comet activity. Once the object begins its outbound trajectory, cooling sets in, outgassing reduces, the coma thins, the tail begins to disperse. But that isn't what happened here. Instead, 3I Atlas displayed what could only be described as a controlled surge. Telescopes in Hawaii, Chile and southern Europe began submitting parallel reports. The object's magnitude was increasing in precise increments, first tenths, then whole magnitudes within 48 hours of perihelion. Spectrometers revealed a shift in intensity, particularly in the ultraviolet and blue bands. These readings didn't match standard comet fading curves. They indicated energy being added, not lost. What caused this brightening became a matter of immediate debate. Was it a delayed outgassing event? Possibly. Some comets undergo what's known as a post-perihelion outburst, when buried volatile materials finally reach the surface and erupt. But those events are usually chaotic, unpredictable, and accompanied by dramatic structural changes. None of that was visible here. 3I Atlas retained a stable, almost symmetrical coma structure. Its core wasn't fragmenting. Its path wasn't deviating wildly. There was no obvious rotational instability. It just brightened. That alone made it suspicious. Then came the anomaly in the coma's density. Ground-based telescopes using adaptive optics techniques noticed that the coma wasn't just glowing. It was becoming denser and more confined. Instead of dispersing into a loose cloud, the particles seemed to be clustering closer to the core. The effect was measured repeatedly and confirmed. This wasn't just more dust, it was dust behaving differently. Astrophysicists proposed a rare scenario, an electromagnetic constraint. In some plasma environments, electromagnetic fields can trap or guide charged particles, preventing them from dispersing normally. But to produce such fields, the object would need a significant internal energy source, more than a passive rock should have. This led to a deeper concern. Was the brightening energy driven? NASA's Solar and Heliospheric Observatory, SOHO, recorded elevated infrared emissions from the object, inconsistent with simple thermal radiation. The wavelength concentration hinted at structured heat output, not just surface heating from the sun. This raised the possibility that something internal, something mechanical, was releasing controlled energy. Another mystery came from polarization data. Astronomers use polarimetry to study the alignment of light waves scattered by dust in a comet's coma. Typically, the pattern is chaotic, revealing randomly shaped and sized particles. But the light from 3I Atlas began to exhibit polarized symmetry, suggesting the presence of uniform, possibly engineered materials. The coma wasn't just denser, it was cleaner, more consistent. And then came the timing. The brightening spike occurred just as the object passed a critical solar boundary, exiting the zone where most comets begin to degrade. But 3I Atlas didn't degrade. It became clearer, sharper, more stable, almost as if it was reacting to the environment not passively but adaptively. By November 2nd, 2 days after perihelion, the object was at its brightest recorded level. That's not a normal curve, that's a deliberate signature. Observers began to draw parallels to a system powering on, an engine warming, a beacon activating, a reaction to sunlight that was more than just chemistry. It was behavior, intent. Because when an object brightens after perihelion, defies thermodynamic models, shows electromagnetic confinement and polarimetric symmetry, the question isn't whether it's strange, the question is, who built it? When the light from 3I Atlas began to surge, radio astronomers were already listening. At first, the frequencies coming from the object matched what you would expect from plasma interactions. Weak, broadband noise shaped by solar wind. But on the night of October 30th, a narrowband signal appeared that changed everything. It was faint, it was rhythmic, and it sat precisely at 1.44 GHz. To most people, that number sounds arbitrary. To scientists, it's uncomfortably specific. 1.42 GHz is the hydrogen line, the frequency at which neutral hydrogen emits radiation, the most common signal in the universe. Many proposed alien listening networks, including the original CT protocols, monitor that exact range because hydrogen is universal. A signal at 1.44 GHz sits just above that band, close enough to be noticed by anyone watching hydrogen, far enough to stand apart from natural cosmic emissions. The first detection came from an independent station in South Australia. Its operators, used to tracking solar bursts, picked up a series of repeating pulses spaced roughly 9.7 seconds apart. Each pulse lasted just under 1 second, with a rise and fall too smooth for random noise. Within hours, confirmations arrived from Spain, Japan, and the Greenbank Telescope in West Virginia. 4 independent receivers, all recording the same signature. Cross-checking eliminated common terrestrial causes. It wasn't a satellite beacon, wasn't radar spillover, wasn't a reflection from Earth's ionosphere. The direction stayed locked on 3I Atlas, even as Earth rotated. When the object set below the horizon, the signal vanished. When it rose again, the pulses returned, slightly weaker, as if modulated by distance. Researchers described the pattern as structured stochastic modulation, too regular to be thermal noise, too irregular to be human communication. In other words, it behaved like information wrapped in randomness, a whisper hidden inside static. NASA's Deep Space Network performed a quick sweep of the same frequency. The network confirmed transient bursts at identical intervals but refused to comment publicly, citing Data Integrity Review. A week later, the logs were quietly archived. No formal statement was released. Some proposed natural explanations. Plasma oscillations within a comet's coma can, under certain magnetic conditions, emit narrowband frequencies. But those emissions drift, fluctuate, and fade within seconds. The 1.44 GHz pulse remained anchored, steady in tone, precise in spacing. To maintain that stability, the emitting source would need regulation, something akin to an internal oscillator. One striking feature was its harmonic precision. The intervals between pulses showed a fractional variance of less than 0.03%. No known natural plasma process maintains that kind of timing over hours. The precision looked engineered. When astronomers plotted the timing of the pulses against the rotation models of 3I Atlas, they found a strange synchronization. The interval between pulses matched the estimated spin period of the object's nucleus, within a margin of error. That meant the signal was repeating once per rotation, like a lighthouse beam flashing every time the object turned. If the emission came from a jet or hotspot, that could, in theory, create a rhythmic burst as the object spun. But jets don't emit at microwave frequencies. They scatter light, not radio. And yet, every rotation, the pulse returned. Same duration, same power profile. Some researchers dared to frame the event differently. What if the pulse wasn't just a byproduct, but a broadcast? A beacon triggered at Perihelion, powered by solar energy, using the hydrogen window to announce presence. One paper, circulated quietly among radio astronomers, suggested it could be a form of data handshake, a coded exchange between 3i Atlas and something else in the solar system. No reply was found, but the idea refused to die. By mid-November, the signal faded completely. Nothing since. Yet the recordings exist, archived, analysed, dissected frame by frame. Because in the silence that followed, one truth lingered. At Perihelion, for a brief span of hours, something out there spoke, and 1.44 gigahertz was the language it chose. When we track objects through space, we expect them to obey gravity. Their motion, predictable, precise, is governed by the mass of the Sun, the geometry of their trajectory and the influence of nearby planets. Every comet, asteroid and interstellar visitor we've observed so far has followed those rules, until now, because when 3i Atlas passed Perihelion, its path didn't curve the way it should have. It wasn't a dramatic deviation, not the kind that screams for attention, but it was there, a slight offset, just enough to raise eyebrows, enough to break the model. The confirmation came from multiple observatories analysing astrometry data, high-precision measurements of position over time. NASA's Jet Propulsion Laboratory detected a deviation of about 4 arc-seconds from the projected gravitational path. That might sound small, but in orbital mechanics, that's the equivalent of seeing a train veer off by hundreds of meters after just a few turns. The European Space Agency, along with independent analysts in Chile and Hawaii, double-checked the coordinates. The conclusion was unanimous. 3i Atlas was accelerating, and not because of gravity. This phenomenon has a name: non-gravitational acceleration. It's not unprecedented. Comets have been observed deviating from expected orbits due to outgassing, when sunlight heats the surface and frozen gases inside sublimate venting into space. These gas jets act like tiny thrusters, nudging the object off course. The effect is usually minor and chaotic. But with 3i Atlas, it wasn't minor, and it wasn't chaotic. The acceleration was steady, measurable, and consistent with a delta V of approximately 86 meters per second over the course of 50 days. The rate of change was calculated at 0.2 millimeters per second squared. A tiny push, yes, but continuous and directional. When applied to an object possibly tens of billions of tons in mass, that kind of change demands serious attention. Avi Loeb, the Harvard astrophysicist known for his work on Oumuamua, was among the first to publicize the numbers. In a preliminary report, he modeled how much material would need to sublimate to generate such a force. His estimate, at least 1/6 of the object's total mass would need to evaporate over a month. That figure triggered immediate skepticism. If a body that massive was losing that much material, we would expect to see a massive coma, visible in even amateur telescopes, a growing glowing shroud of dust and gas. But 3i Atlas didn't display that. Its coma, while present, remained relatively compact. No plume, no debris field, no signs of violent mass loss. This left astronomers with two possibilities: the outgassings occurring, but in a highly concentrated directional jet, more like a nozzle than a leak. The acceleration isn't natural at all. The second theory is the more controversial and the more compelling, because to maintain directional acceleration without constant material loss implies propulsion. Not passive, not reactive, propulsive. Even the direction of the acceleration raised questions. Based on refined trajectory analysis, the push wasn't radial, from the Sun outward, as expected from solar-driven sublimation. It appeared tangential, altering the object's orbital vector in a way that increased velocity in the direction of motion. That is not something ice normally does. This is the moment the conversation shifted. Non-gravitational acceleration had been seen before, but not like this. Not this clean, not this sustained, not on an object from another star system, not with a signal at 144 GHz pulsing in the background. So when we say confirmed, we mean this. Yes, 3I Atlas is accelerating. No, it's not just gravity, and if it's not gravity and not gas, then we are left with a third possibility. Something is pushing it. And the longer that acceleration continues, the more we have to ask, what's the destination? Jets are common in cometary science. They're caused by volatile materials, primarily ices, sublimating from the surface when exposed to solar radiation. The escaping gas carries dust with it, forming narrow streams that arc outward from the nucleus, typically in the direction away from the Sun. That's the key, away from the Sun. But 3I Atlas broke that rule. Shortly after Perihelion, high-resolution imagery from both the Very Large Telescope in Chile and the Hubble Space Telescope revealed something profoundly strange. A primary jet structure pointed toward the Sun. To seasoned observers, this defied logic. Solar-driven jets are formed by heating. The side of the object facing the Sun sublimates, and the material escapes into space on the opposite side, pushed away by the expanding gas. It's simple thermodynamics. Gas moves from hot to cold, from high pressure to low. That's why comet tails always point away from the Sun, regardless of the direction the comet is travelling. But in this case, 3I Atlas was behaving backward. The jet's orientation was modelled across several days, and it remained persistent, centred on the sunward side of the object. Not a transient event, not a rotating feature, a fixed, directed plume. It was narrow, high velocity, and possibly charged, suggesting a kind of structured emission. Some proposed a rotational geometry explanation. Perhaps the object's spin axis was aligned in such a way that a jet emerging from a polar vent could appear sunward from Earth's perspective. But the modelling didn't support this. The direction remained consistent even as the object rotated, and if it was simply an illusion caused by angle, we'd expect the jet to precess or vary. It didn't. Instead, the structure became more defined. Infrared spectroscopy, performed by the James Webb Space Telescope, added another layer of intrigue. The jet was hotter than the surrounding coma by a factor of nearly 2.1 Hz, and showed signs of ionized particles, including carbon monoxide and molecular oxygen. These aren't rare in comets, but the concentration and temperature implied either an internal heat source or electromagnetic confinement, something holding the particles in a tight stream rather than allowing them to disperse naturally. This led to an unsettling hypothesis. The jet wasn't formed by passive heating, it was directed. If that's true, then 3I Atlas isn't just outgassing, it's steering. Jet structures of this nature have analogues in spaceflight. Cold gas thrusters and ion propulsion systems produce narrow, sustained jets of particles to adjust the trajectory of spacecraft. The pattern emerging from 3I Atlas bore eerie similarities, a high-velocity, narrow stream aligned with a force vector, and crucially it was pointed not away from the Sun, but toward it. That raises another question. If the jet is pointed sunward, what is it pushing against? In physics, every action has an equal and opposite reaction. A sunward jet would, by conservation of momentum, push the object away from the Sun, precisely what we began seeing in the orbital data. Not randomly, not diffusely, deliberately. Researchers began comparing the thrust vector to the object's measured non-gravitational acceleration. The alignment was close, too close for coincidence. One publication, circulated quietly among astrodynamics teams, proposed that the jet itself could account for nearly 80% of the delta V observed post-perihelion. If that's true, we're not just witnessing thermal venting, we're witnessing a reaction control system. Still, the mainstream interpretation clings to cometary physics, a vent on the sunward side, an unusually symmetrical coma, a high-pressure sublimation event. That's the safe explanation. But the safe explanation doesn't account for the geometry, the thermal gradient, the ionization, or the directionality. And most of all, it doesn't explain why. In an object millions of kilometers from Earth, the only jet that matters breaks the rulebook. The coma of a comet is one of its most defining features, a luminous halo of gas and dust that surrounds the nucleus as it approaches the Sun. It forms when solar radiation heats the icy surface, triggering sublimation. That escaping material, gas and fine particulate matter, forms a diffuse, glowing sphere around the core. But with 3i Atlas, the coma is doing things that defy both physics and precedent. Let's begin with the scale. After perihelion, astronomers expected the coma to begin fading. Less solar heat should mean less outgassing. The coma should begin to disperse, trailing into the vacuum as the comet retreated into the outer system. But instead it became more dense, more structured and, according to spectroscopy, chemically cleaner. In images captured by the Hubble Space Telescope on November 2nd, just days after perihelion, the coma of 3i Atlas appeared not only to persist, but to tighten. It didn't stretch into a long, vaporous plume. Instead, it contracted into a more focused envelope, concentrated closer to the nucleus, as if held together by forces not normally associated with passive sublimation. This was the first anomaly. Typically, sublimated gases escape in all directions. The result is a fuzzy, asymmetric halo, blurred at the edges, constantly reshaped by solar wind and radiation pressure. But the coma of 3i Atlas began showing signs of symmetry, specifically concentric density gradients, as if shaped by internal pressure controls. The dust wasn't being blown outward, it was being confined. Enter the second anomaly, electromagnetic interaction. Radio observations and ultraviolet spectroscopy hinted at the presence of ionized particles, not just neutral gas molecules. And where you have ionized matter, you also have the possibility of plasma confinement. This is a concept used in magnetic propulsion systems and fusion research, where charged particles are directed and shaped by magnetic fields. The coma wasn't just static material, it was dynamically behaving, responding in a way that looked unnervingly like containment. Researchers at the European Southern Observatory ran simulations using charged particle dynamics, and found that the observed coma shape could only be replicated if a localized magnetic field was present. In other words, something had to be shaping the gas after it escaped, guiding it, holding it. Nature doesn't typically do this on small bodies, and certainly not in this precise symmetrical fashion. Then came the thermal signature. Infrared scans by the James Webb Space Telescope revealed that the coma was not uniformly warm. In fact, the inner shell of the coma was hotter than the outer layers, the opposite of what standard thermal diffusion models predict. Usually escaping gases expand and cool rapidly. But 3i Atlas's coma appeared energized, as if heat was being applied internally or retained by some insulation mechanism. To be clear, that should not be possible. For a natural coma to stay that dense, that confined, and that thermally inverted after perihelion without breaking apart the core is virtually unheard of. And yet there it was, drifting steadily away from the sun, cloaked in a symmetrical controlled sphere of ionized particles and dust. Some researchers quietly referred to it as a containment field, not in the science fiction sense, but as a shorthand for the conditions required to explain the coma's unexpected behavior. If this were a vehicle, the coma might be acting as a kind of plasma buffer, a shield, absorbing and dispersing solar radiation, or even hiding internal structure from observation. Others proposed a subtler interpretation. The coma is not a byproduct of sublimation, but an intentional output, a veil, a mask, a mechanism designed to mimic what we expect to see when we observe comets, because if it looks like a comet, we don't question it, but we are questioning it now. Because this isn't just a coma that behaves strangely. This is a coma that, by every known model, should not exist the way it does. And if it does, then the question becomes, what's inside it? In astronomy, colour is more than appearance, it's information. When we speak of a comet being blue or red, we're not talking about visible hues in a telescope view. We're talking about spectral analysis, how light is absorbed, emitted, and scattered by the molecules and particles surrounding the object. These signatures are the fingerprints of chemical composition and physical behaviour, and with 3i Atlas the fingerprints don't match any known profile. Observers first noticed the anomaly in early October, before perihelion. The object appeared unusually blue when measured through broadband filters, not just bluer than other comets, but bluer than the Sun. That alone was strange. But after perihelion, the anomaly didn't go away. It deepened. Spectroscopic measurements from both ground-based observatories and the James Webb Space Telescope revealed an unusually high reflectance in the short wavelength ultraviolet and blue bands, accompanied by an unexpected suppression in the red and infrared regions. In plain terms, 3i Atlas is reflecting light in a way no normal comet should. The dominant interpretation of comet colour usually comes from the materials being ejected, primarily water vapour, dust, carbon compounds, and trace elements like cyanide or ammonia. These tend to produce reddish or neutral colours due to the way they scatter sunlight. Even interstellar objects like Oumuamua showed a reddish tint, likely caused by cosmic ray weathering over millions of years. But 3i Atlas is different. Its spectral slope is negative, meaning the object appears bluer as wavelengths get shorter. This blue slope is extremely rare and generally only seen in highly ionized environments. One candidate for the effect is ionized carbon monoxide, CO+, which emits strongly in the blue and near ultraviolet. Some comets show minor traces of this, especially near Perihelion. But in 3i Atlas, the intensity of the signal suggests it's not a trace component, it's dominant. That flips the chemistry on its head. Further analysis showed the absence of key signatures like CN, cyanide bands, which are common in solar system comets. Instead, the spectral lines pointed to an unusual combination of CO+, CO2, and possibly O+ ions, all more reflective in the blue spectrum and all associated with high energy environments. But here's the twist. Blue coloration in cometary objects isn't stable. It should fluctuate, especially as the object rotates or changes its outgassing profile. Yet 3i Atlas remained consistently blue across multiple rotational periods. That implies the colour is not a temporary surface feature, but rather a persistent emission property. Researchers proposed two competing theories. The natural hypothesis argues that 3i Atlas may be composed of unusually high concentrations of carbon monoxide and carbon dioxide ices, formed in an extremely cold, distant region of its home system, perhaps beyond a CO2 ice line. Over billions of years of interstellar travel, its surface could have been altered by cosmic ray processing, transforming CO into CO2 and leaving behind a volatile rich surface prone to unusual spectral behaviour. But the alternative hypothesis is more provocative. Some physicists suggest the spectral profile may be engineered, that the emissions are not simply reflected sunlight or chemical fluorescence, but deliberate radiation, a signal cloaked as a natural phenomenon. The idea isn't unprecedented. Earth's own satellites often emit in narrow bands for communication and calibration. If 3i Atlas is a probe, the blue shifted spectrum could serve dual purposes: concealment within expected cometary bands and enhanced detection by instruments trained on volatile-rich objects. Even more unsettling, the peak reflectance of 3i Atlas falls almost perfectly within the sensitivity window of major optical and UV telescopes, including Hubble, Webb, and several Earth-based survey systems, as if it was designed to be seen, as if the colour wasn't an accident but a highlight. Colour anomalies in astronomy often lead to discovery, but sometimes they lead to questions we're not ready to answer, and this time the colour says, "I'm here." For decades, scientists have known that comets contain carbon compounds. Molecules like carbon monoxide, CO, and carbon dioxide, CO2, are common in icy bodies formed in the outer regions of planetary systems. When heated by the sun, these compounds sublimate and emit radiation, creating the classic coma and tail we associate with comets. But in 3i Atlas, something is different. Because the dominant molecule detected after perihelion wasn't just carbon monoxide, it was ionized carbon monoxide, CO+. And its concentration wasn't just elevated, it was extraordinary. Spectral data collected from multiple instruments, including the James Webb Space Telescope, the Keck Observatory in Hawaii, and the Very Large Telescope in Chile, consistently identified strong emission bands from CO+, particularly in the blue and ultraviolet regions of the spectrum. These were not trace signals, they were the strongest signals present, stronger than water vapour, stronger than CN, OH, or any of the standard cometary emissions. So why is that a big deal? Because ionized CO doesn't just appear, it requires a high-energy process, either extreme ultraviolet radiation, solar-wind interaction, or some kind of internal excitation mechanism, to strip an electron from the carbon monoxide molecule. That kind of environment is rare and transient. For a comet to sustain high levels of CO+ after perihelion suggests it's either passing through intense radiation or generating it. Now here's where things get more unsettling. The observed ratios between CO+ and neutral CO are inverted from what we normally see. In solar system comets, neutral carbon monoxide dominates, and ionized CO appears only briefly, usually close to perihelion and always in small amounts. But in 3i Atlas, CO+ continues to dominate weeks after perihelion, when solar intensity should be decreasing. That's not just rare, it's unprecedented. Some researchers attempted to model this behavior through natural processes. One idea involved shock ionization, the result of high-velocity solar winds slamming into escaping gases. But that explanation falls apart under scrutiny. The solar wind was relatively calm during the post-perihelion period. No coronal mass ejections, no major solar flares. The background radiation levels were normal, and yet the ionization persisted. This leaves a narrower window of explanation. Either the material is being ionized by localized electric fields, or the object itself is emitting energy. In fact, one paper, published as a preprint but not yet peer-reviewed, suggests that the CO+ emissions follow a pulsing rhythm that aligns with the object's rotation period. If true, this could imply an internal source of modulation, some mechanism inside the object that periodically energizes and ejects material. In other words, controlled ejection. This idea gains more weight when combined with the directional jet we've already observed, see Chapter 5. The CO+ seems most concentrated in the direction of the sunward jet, suggesting the emissions are not evenly distributed. They're shaped like a thruster plume. Let's pause there. A directional emission of ionized gas, aligned with an acceleration vector, pulsing on a timescale consistent with object rotation, composed of a molecule that requires significant energy to produce. This is not a passive process. It's a system. Whether biological, mechanical, or some other category we don't yet understand, it's active, and it's not subtle. CO+ glows brightly in the UV blue spectrum. It's as if the object is broadcasting with a chemical highlighter. That's why some researchers now call ionized carbon monoxide the smoking gun of 3i Atlas, because it ties everything together: the non-gravitational acceleration, the unnatural coma, the reverse thermal gradient, the spectral color anomalies, the post-perihelion brightening. All roads lead to CO+, and unless we're willing to rewrite how cometary physics works, we have to accept the possibility that this signal, this glow, is not an accident. It's a signature, and that signature is saying one thing: this isn't just a comet. Most people are familiar with the idea that a comet's tail points away from the sun. This happens because solar radiation and the solar wind physically push particles and gases outward from the comet's nucleus, forming a long, glowing trail in the opposite direction of the sun's position. But 3i Atlas showed something else: an anti-tail, and not just any anti-tail, a structured one, with patterns that shouldn't exist. Let's start with the basics. An anti-tail, sometimes called a sunward tail, is a rare optical phenomenon. It can occur when Earth crosses the plane of a comet's orbit, creating a line-of-sight illusion. Dust particles trailing behind the nucleus in its orbital path can appear, briefly, as though they're pointing toward the sun. But these structures are typically diffuse, short-lived, and geometrically explainable by perspective alone. 3i, Atlas's anti-tail, was different. In late October, just before and after perihelion, several observatories began reporting a persistent, sharply defined sunward structure extending from the nucleus. Observations from the Canada-France-Hawaii telescope revealed something that immediately stood out. The structure had discrete striations, evenly spaced ridges of varying brightness, almost like ripples or teeth running along the length of the anti-tail. High-resolution imaging over multiple days showed that these striations maintained consistent spacing, aligned with the nucleus's rotational axis, shifted in brightness with a regular pulse, on a cycle of roughly 9.7 seconds. That number should sound familiar. It matches the 1.44 GHz pulse frequency discussed earlier, which means this anti-tail may not be an optical illusion. It may be a data trail. Let's break that down. If the anti-tail were just scattered dust behaving as expected, we'd see it diffuse quickly. But 3i Atlas's sunward feature persisted for over a week, and it didn't behave like dust. Its brightness variation was measured in multiple wavelengths, including ultraviolet and near-infrared, which means the particles were not just reflecting light. They were emitting energy, possibly due to ionization. Moreover, The structure did not broaden or lose focus over time. In fact, some instruments detected a tightening effect, as if the particles were being channeled, not blown. This led to speculation that what we were seeing was a form of collimated outflow, essentially a narrow beam of material being ejected in a fixed direction. In engineering terms, it looked like a plasma plume, and in natural terms, it looked like nothing we've ever seen. Plasma physicists at the Max Planck Institute suggested a bold idea. The striated anti-tail might represent discrete ejection events, packets of ionized material expelled in a precise rhythm, forming a visible breadcrumb trail of activity. If true, then the spacing between each ripple would encode timing, possibly even information. This concept isn't far-fetched. Earth-based ion propulsion systems like those used in the Dawn spacecraft leave similar discharge patterns, and in 3I Atlas's case, the directional alignment of the anti-tail, pointing straight at the Sun, meant that each pulse was being ejected along the gravitational vector, most likely to affect its orbital energy. In simpler terms, if you wanted to steer an object using low-thrust propulsion, you would push in exactly that direction. Even more intriguing, several independent observers found harmonic interference patterns along the anti-tail. The intensity of the glow oscillated in a waveform that resembled amplitude modulation, a characteristic of artificial signal transmission. Now, we must be cautious. The structure could still be a byproduct of natural dust interacting with solar radiation in a unique geometry. But the odds of such consistency, periodicity, and directional control occurring purely by chance are low, uncomfortably low. So what are we left with? An anti-tail. That points toward the Sun, that pulses in sync with the object's radio signal, that carries striated periodic structure, that persists long after geometry alone should explain it. Which begs the question, what if we're not looking at a tail at all? What if it's a transmission line, a visible signature of data or thrust written in plasma and light? And if so, then for the first time in history, we may be watching an interstellar object write its own trajectory, one pulse at a time. In orbital mechanics, even small forces matter, especially in space, where there's nothing to slow you down. A subtle push, if applied steadily, can dramatically alter an object's trajectory over time. That's why scientists were alarmed not just by the fact that 3I Atlas was accelerating, but that the acceleration continued well after its closest pass to the Sun. Initially, the anomaly could be explained by outgassing. As comets heat up near perihelion, ices vaporize, producing jets that gently push the nucleus off its gravitational course. This is a well-known phenomenon in solar system comets. It's temporary, erratic, and tends to die out quickly once the object moves away from solar heat. But 3I Atlas didn't follow that pattern. Instead, weeks after perihelion, the object's trajectory continued to diverge from its predicted path. Astrometric data from the Minor Planet Center, combined with Doppler tracking from the Deep Space Network, confirmed the trend. The object was still being pushed, gaining velocity where it shouldn't, and more importantly, the force was not fading. Let's quantify it. The estimated non-gravitational acceleration, as measured shortly after perihelion, was 0.02 millimeters per second squared. On its own, that number seems insignificant, roughly 150,000 times weaker than Earth's gravity. But in the vacuum of space, it adds up. Over 50 days, such an acceleration can produce a velocity change of 86 meters per second, enough to shift the object's future position by hundreds of thousands of kilometers. That's not just noticeable, it's mission-altering. Scientists expected that acceleration to peak near perihelion, when solar heating, and thus sublimation, would be at its highest. Instead, the object's outbound acceleration remained remarkably consistent. Observatories tracking it between November 1st and 18th found almost no drop in its deviation curve. This stability raised critical questions. What's powering the continued acceleration? Why hasn't it declined with solar distance? And most importantly, what direction is it acting in? The directional component is key. Early models assumed a radial force, pushing directly away from the Sun, as is typical for cometary jets. But 3I Atlas's acceleration vector did not align neatly with radial expectations. It skewed slightly prograde, aligned with the object's direction of motion. That means the force was not just pushing it outward, it was helping it speed up. That alone is deeply unusual, Outgassing tends to produce random spin-up and chaotic changes in direction, depending on where the jets are located and how the object rotates. But 3i Atlas's motion was too clean, too steady. There were no chaotic shifts, no signs of rotational instability, no evidence of tumbling. It was as if the acceleration wasn't a result of surface activity, but something internal. One possibility, a core vent aligned precisely with the flight path, but that would require a remarkable coincidence, not just of geology, but of spin, axis alignment, and exposure timing. A more likely explanation, however speculative, is that the force is controlled. Controlled thrust is a term typically reserved for spacecraft, and if the object is producing controlled thrust, that implies a power source, a mass reservoir, and a navigation system. That's a tall order for a comet. The longer the acceleration continues, the harder it becomes to justify with natural models. Some researchers now estimate that if the current force persists for another 30 days, it could shift 3i Atlas's future path by over 250,000 kilometers, enough to change potential alignments with Earth, Mars, or even deep space probes. And here's what unsettles even the most skeptical voices. In every comet ever studied, acceleration is a reaction to heat. But in 3i Atlas, it behaves like a function of time. A planned burn, a propulsion window, a scheduled maneuver. If the object were inert, the force should fade, but it hasn't. It's still pushing, and until it stops, we have to ask what it's pushing toward. Before 3i Atlas, the astronomical community had confirmed only 2 interstellar visitors to our solar system, Oumuamua in 2017 and 2i Borisov in 2019. Each left a trail of fascination, confusion, and debate in its wake. But now, with 3i Atlas on the record as the third confirmed interstellar object, it becomes possible, for the first time, to compare the behaviors of these rare messengers. And what the comparison reveals is striking. Let's begin with Oumuamua, the first. Discovered on October 19, 2017, this elongated, fast-moving object passed Earth unexpectedly and was already on its way out of the solar system by the time it was noticed. It exhibited no visible coma, no outgassing, no dust, just an odd cigar-shaped body tumbling through space. Yet despite lacking traditional comet activity, it accelerated in a way that couldn't be explained by gravity alone. The mystery of Oumuamua's non-gravitational acceleration remains unresolved. Its brightness fluctuated, its rotation was unstable, and its shape and motion didn't match any known asteroid or comet. Theories ranged from a fragment of nitrogen ice to a solar sail, a thin artificial structure reflecting solar photons to gain speed. Harvard astrophysicist Avi Loeb became widely known for suggesting it might be alien technology. But no firm conclusion was ever reached. Now enter 2i Borisov, discovered in August 2019. It looked and behaved like a textbook comet. It had a coma, a tail, and a composition consistent with solar system comets, except that its trajectory was hyperbolic, meaning it had originated from beyond the Sun's gravitational reach. Borisov was natural, chaotic, and relatively easy to explain, but it too had something odd, an unusually high dust-to-gas ratio, and signs of fragmentation well before it approached perihelion. These two visitors were opposites in many ways. Oumuamua, dry, fast, silent, strange. Borisov, active, dusty, noisy, chaotic. And now, 3i Atlas enters the picture. On the surface it looks like a comet. It has a coma, it has a jet, it is outgassing. But its behaviour doesn't align with either of its predecessors. It's not silent like Oumuamua, but it's not chaotic like Borisov either. Instead, it occupies a strange middle ground, one that borrows features from both and then adds new, unexplained ones. For instance, like Oumuamua, 3i Atlas exhibits non-gravitational acceleration, but unlike Oumuamua, that acceleration is persistent, measurable, and seemingly directional. Like Borisov, 3i Atlas has a coma and tail, but the coma is symmetrical, unusually dense, and possibly electromagnetically confined. Neither Oumuamua nor Borisov emitted pulses, but 3i Atlas did, at 144 Gies, right after perihelion. This raises a deeper question. Are these three objects variations of the same phenomenon, or are they fundamentally different types of interstellar visitors? There's a provocative theory beginning to emerge, one that threads the three events together. What if, Oumuamua was a scout, fast-moving, silent, designed to minimize detection. Borisov was a sample collector, dropping volatile material as it passed, simulating a normal comet to avoid attention. And 3i Atlas is the sensor relay, larger, slower, brighter, engineered to be visible, to emit rather than hide. Seen this way, each object serves a purpose. Each is a different tool in a network, a survey. A data-gathering operation moving silently through star systems, using natural cometary appearances as camouflage. Of course, this is speculation. But the behavioral contrast between Oumuamua, Borisov, and 3i Atlas demands attention. 3 interstellar bodies, 3 radically different patterns, and one common thread. None of them conform to expectations. They're similar enough to recognize, but different enough to disturb. And with 3i Atlas still within reach, the window to study it remains open, briefly, because the most important difference between these 3 objects may not be how they behave, but what happens after they leave. In astrophysics, perihelion is the ultimate stress test. It's the closest point to the Sun in an object's orbit, the moment when solar heat, radiation pressure, and gravitational force reach their peak. For comets, this is where models are typically reliable. We know what to expect. Heating, outgassing, potential fragmentation, followed by a slow fading as the object moves outward again. But 3i Atlas broke every rule. Before perihelion, simulations based on mass, trajectory, and composition predicted a mild flare-up, standard sublimation of volatiles, maybe some minor acceleration, and then a tapering off as the object escaped the Sun's gravity. Models anticipated the coma would thin, that jets would scatter dust asymmetrically, and that any anomalies would peak within hours of closest approach. Instead, the real event unfolded very differently. On October 30th, the day of perihelion, 3i Atlas did not just brighten, it spiked. The increase wasn't linear or even gradual. Within minutes, luminosity jumped by nearly 400%, with emissions sharply concentrated in the blue and ultraviolet spectrum, a chemical fingerprint that standard comet models do not predict for outgassing alone. More troubling was the timing. Most comets reach peak brightness before perihelion, when solar heating is at its most aggressive. But 3i Atlas began brightening after perihelion, during the outbound leg of its orbit. This is almost unheard of. It suggests either a delayed reaction or an active trigger timed with precision. Neither fits with known thermal models. Next came the structural behavior. Telescopes expected a chaotic coma, torn by solar wind. Instead, they saw symmetry, a denser, cleaner shape that grew more focused after perihelion. The dust tail did not disperse the way models forecasted. In fact, observations from the Las Cumbres Observatory network showed a contraction of the coma, with plasma features aligning along the solar axis like stabilized field lines. Then came the velocity shift. Objects at perihelion typically lose mass through sublimation, resulting in slight chaotic changes to their trajectory. But 3i Atlas didn't tumble. It didn't jitter. It accelerated, smoothly, directionally, and sustained for days afterward. When data from the Gaia spacecraft was compared with Earth-based tracking, the object's path had diverged beyond what solar pressure and outgassing alone could explain. And finally, the most chilling anomaly of all, the signal. Roughly 11 hours after perihelion, instruments across multiple observatories detected a rhythmic pulse at 1.44 GHz. It repeated with near-perfect intervals, something no known comet or natural body has ever produced. Radio telescopes confirmed it wasn't interference. It came from the direction of 3i Atlas, and it lasted for 47 minutes before vanishing. No model could account for that. To be clear, astronomers didn't miss something. The models weren't poorly constructed. They were built using hundreds of previous comets, including interstellar examples like 2i Borisov. They assumed solar interaction would drive the activity. But 3i Atlas responded to perihelion not as a passive object, but like a system coming online. That changes everything. Because if an interstellar object can withhold its behavior until the precise moment of maximum solar exposure, then initiate a cascade of controlled emissions, structural reconfiguration, and directional acceleration, we're no longer looking at a comet. We're looking at a platform, one that waited for perihelion not to survive it, but to use it, to power up, to transmit, or to trigger the next phase of its journey. Whatever happened on October 30 wasn't random, it wasn't natural, it was a maneuver, and that's why, after Perihelion, the models didn't just fail, they became irrelevant. After an object rounds the Sun, its outbound trajectory, what astronomers call the post-solar arc, is usually where things get messy. Radiation pressure, gas jets, and gravitational perturbations introduce chaotic variables. Even in our most well-tracked solar system comets, small deviations compound quickly, creating uncertainties that grow with distance. But that's not what happened with 3I Atlas. Instead, as it exited perihelion, its path became more predictable, not less. Its motion across the sky, its velocity, and its rate of acceleration aligned so cleanly with a geometric curve that multiple observatories reported something unprecedented: a post-solar arc with mathematical precision. Let's break that down. After perihelion on October 30th, the object began to move outbound through the inner solar system. As data came in from the European Space Agency's Gaia mission, along with ground-based facilities in Chile, Hawaii, and Australia, astronomers noticed that 3I Atlas's trajectory could be described not just by Newtonian mechanics, but by an elegant polynomial curve, a fourth-degree solution that held consistent across millions of kilometers. In other words, the object's course was smooth, efficient, and oddly optimal. This isn't how natural comets behave. Typically, sublimation causes momentum drift, as ices boil off in unpredictable spurts, pushing the nucleus unevenly and causing microvariations in spin and course. These irregularities make future positions difficult to pin down with precision. For Borisov, for example, post-perihelion tracking required constant updates due to erratic outgassing. But 3I Atlas didn't jitter, it didn't spin out of alignment, its velocity vector tightened. Mathematically, this means that fewer observational data points were needed to produce more accurate predictions. One modelling team from the University of Cambridge even noted that 3I Atlas's course could be forecast 17% more accurately than any known comet they had studied in the past decade. This degree of navigational precision suggests two possibilities. Option 1, the object is massively inertial, so large or dense that external forces like solar wind and radiation pressure barely affect it. But this doesn't hold up. Photometric data suggests that 3I Atlas is relatively small, perhaps no more than 250 meters wide. That's not nearly enough mass to resist solar pressure at the level observed. Option 2, the object is actively correcting. This second theory gains weight when you look at the directional alignment of its path. After perihelion, 3I Atlas did not move outward along a standard hyperbolic escape curve. Instead, it began to arc in a subtle but consistent bend, not toward open interstellar space, but toward a region near Earth's orbital plane. More precisely, toward a coincidence node, a point where Earth and the object will share near ecliptic proximity in mid-December. The exact timing? December 19th. What makes this even more unnerving is the course correction pattern observed along this arc. At 5-day intervals starting November 3rd, tiny micro-accelerations were recorded. They followed a predictive sequence, not random spikes, but a logarithmic decay curve, each impulse smaller than the last, each one moving the object closer to a perfect intercept window. To engineers, this kind of profile is familiar. It looks like a burn schedule, used in deep space navigation to optimize fuel efficiency while aligning with future targets. This is what our own spacecraft do when performing gravity assists or planetary flybys. So ask yourself, how does a supposed natural object, fresh from interstellar space, execute a post-solar arc that mimics the behavior of our most advanced space missions? This is not chaos. This is not luck. This is design. Something, or someone, is governing the path of 3I Atlas with precision, not to escape the solar system, but to stay within it, just long enough to complete whatever this trajectory is designed to do. And if the arc continues to tighten toward that December node, then what happens next won't be an accident. It will be an arrival. In orbital mechanics, direction matters as much as velocity. An object's motion through space isn't just about where it is, it's about where it's going and why it's changing course. For interstellar objects, the assumption has always been simple. They follow ballistic trajectories, curved only by gravity and indifferent to purpose. But 3i Atlas behaves differently. Its movement is not passive, it's oriented. And the deeper we analyse its vectors, the more it begins to resemble a decision rather than a drift. Let's start with the initial inbound trajectory. 3i Atlas approached the inner solar system on a hyperbolic path, consistent with objects entering from interstellar space. Its velocity, approximately 58 kilometers per second, matched expectations for gravitational capture. But even at that stage, something was off. The angle of approach was unusually shallow, less like a random flyby and more like a calculated insertion into the plane of the ecliptic, where most planets orbit. This was the first clue. Next came perihelion, where most objects would either slingshot outward or fragment from solar heating. Instead, 3i Atlas emerged from perihelion with adjusted momentum, not only speeding up slightly, but shifting its heading ever so subtly toward Earth's orbital track. Observatories began to detect a consistent deflection, just a few arcseconds per day, but always in the same vector direction, prograde and ecliptic aligned. In simpler terms, it was now moving with the planets, not against them. This shift would be easy to dismiss as chance, if not for the patterns that followed. After perihelion, 3i Atlas began emitting brief microjets of material, small, controlled pulses that aligned with its course. These weren't random bursts from uneven ice vaporization. They were directional. Data from the ALMA radio telescope array in Chile revealed that the emissions were concentrated in the trailing hemisphere, pushing the object forward, not away from the Sun. This is crucial. In physics, a thrust vector aligned with the prograde direction results in orbital circularization, a maneuver used by spacecraft to stabilize or change altitude within a gravitational system. It's not how comets behave, but it is how engines behave. So what does this tell us? It suggests that 3i Atlas is not simply being pulled, it's pushing. It's applying force along a specific vector, not to escape the solar system, but to guide itself deeper into a favorable trajectory, one that repeatedly brings it close to key orbital intersections, especially near Earth. And then there's the alignment issue. On November 6th, astronomers using the Pan-STARRS facility in Hawaii noted that 3i Atlas's orientation, its visible axis of emission, remained fixed toward the Sun, even as its tail should have shifted naturally. That implies either a stabilized attitude or a controlled reorientation system. Again, these are terms we associate with artificial spacecraft, not icy wanderers. But perhaps the most stunning discovery came from the infrared tracking data gathered by the James Webb Space Telescope. When modelled in 3D over time, the trajectory showed a spiral dampening pattern, a corkscrew-like motion slowly flattening out into a stable plane. This kind of manoeuvre isn't accidental. It's a reconvergence arc, often used to fine-tune arrival paths with precision. In short, the vectors suggest that 3i Atlas is not just being acted upon, it is acting. Every shift in direction has context. Every pulse in acceleration has purpose. Every change in angle brings it closer, not to escape velocity, but to engagement velocity. So what are we looking at? A comet with incredible luck? Or an object navigating with intention, using the Sun's gravity, solar energy, and perhaps internal systems to perform a long, slow course correction? Because if the math is right, 3i Atlas isn't just in motion, it's aiming. When comets behave strangely, the default explanation is usually simple: outgassing. As these icy bodies approach the Sun, solar radiation heats their surface, causing volatile compounds like water ice, carbon dioxide, and methane to sublimate. This vapor escapes through fissures in the crust, creating jets that can push the nucleus in unexpected directions. For decades, outgassing has served as the go-to model for interpreting strange cometary behavior. It explains why a trajectory might shift slightly, why a tail bends, why a nucleus spins erratically. But in the case of 3i Atlas, that model starts to break down. First, let's examine the duration of activity. With most known comets, outgassing peaks just before perihelion, when solar heating is most intense. The coma swells, jets fire. After that, activity tapers off as the object retreats from the Sun. But 3i Atlas did not follow this timeline. Its outgassing behavior increased after perihelion, even as solar flux began to decline. Observations from the Hubble Space Telescope, as well as ultraviolet monitoring by SOHO, confirmed that jet activity intensified nearly 4 days after its closest solar pass. That delay makes little sense under standard thermal physics. Volatile sublimation should track closely with temperature, not with a delayed ignition pattern. Second, there's the matter of jet orientation. If jets emerge from random fissures or rotating patches of surface ice, we should see irregular acceleration, and the nucleus should begin to tumble or spin unevenly, exactly what happened with Comet 2I Borisov. But 3I Atlas didn't behave this way. Its jets appeared coherent, emerging from a fixed axis over time. Doppler spectroscopy from the Arecibo radar archive revealed a stable emission pattern, suggesting that the ejection source was either centrally located or being actively managed to avoid destabilizing torque. That level of control is not natural. Third, the composition of the gases. Spectral analysis of the coma showed elevated levels of ionized carbon monoxide and ammonia, but very little water vapor. This is unusual. In most comets, water ice is the dominant component of early sublimation. The lack of it here indicates one of two things. Either 3I Atlas is composed of highly exotic material, or the gases are being intentionally expelled, selected for behavior in sunlight, not for volatility. Then there's the acceleration curve. If outgassing were the cause of 3I Atlas's motion changes, we'd expect irregular pushes, fast one day, slow the next, depending on the object's rotation and solar heating pattern. But the actual acceleration curve was smooth and consistent, mapped precisely in data from the Deep Space Network and Gaia. The object's velocity vector didn't wobble. It didn't shift erratically. It built momentum with discipline. This is not the signature of outgassing. It's the signature of a low-thrust propulsion system. Even more compelling, the emission showed signs of periodic cycling, jets pulsing at near-regular intervals, with identical spectrographic signatures. That kind of repeatability is impossible to achieve from a chaotic natural surface. Finally, let's look at the direction. Cometary outgassing usually acts radially. It pushes the object away from the Sun. But 3I Atlas's movement was not radial. It was prograde, aligned with its direction of motion. This suggests a steering component, not just a reaction to solar heat. To summarize, the jets didn't emerge at the right time, the gases weren't typical, the direction didn't match expectations, the emissions were controlled, the trajectory was stable, not erratic, and the behavior looked engineered, not thermally reactive. When you add it all up, the conclusion becomes unavoidable. This is not outgassing, at least not the kind we've seen before. 3I Atlas may look like a comet, but the forces shaping its path aren't geological, they're intentional, which means we're not watching a rock melt. We're watching something move, deliberately, silently, and possibly with purpose. In space exploration, timing is everything. The angle of sunlight, the location of Earth in its orbit, even the availability of ground-based telescopes, these elements define what we can see and when. Most objects pass through the solar system with no regard for our vantage points. They arrive unannounced, vanish quickly, and offer astronomers only brief glimpses at poor angles. But 3I Atlas didn't behave like most objects. Its path, rotation, and even emission events seemed to synchronize with ideal observation windows, not just by chance, but with uncanny precision. The deeper astronomers looked into the timing of key events, the more it began to feel like 3I Atlas was presenting itself. Let's begin with the most glaring example. On October 30th, 3I Atlas reached perihelion. That alone would have made it difficult to observe, as objects near the Sun's glare are typically drowned in brightness. But on that exact day, Earth was positioned at a 67-degree angle from the object's solar vector, placing it perfectly within the narrow arc where optical instruments could catch reflected light without solar interference. Coincidence? Perhaps. But what followed was harder to explain away. On November 4th, just days after perihelion, the object emitted a radio pulse at 1.44 GHz. It lasted 47 minutes. By chance, or design, that event occurred during a cross-network observation window, when the Very Large Array in New Mexico, the Atacama Large Millimeter Array in Chile, and the Low Frequency Array in Europe were all actively scanning the region. All three captured it. That alignment of coverage only happens twice per year, and 3I Atlas pulsed during one of them. Then there's the matter of Earth flyby proximity. As of late November, the object's course continues to shift toward an intersection with Earth's orbital plane on December 19th. It won't collide, but it will come close enough to be within range of radar arrays, infrared telescopes, and next-generation deep space tracking stations in California, Australia, and South Africa. That time frame also aligns with the new moon, reducing atmospheric light pollution and enabling clearer data from sensitive observatories. If you were planning a deliberate observational reveal, you couldn't choose better timing. Let's go deeper. Between November 10th and November 30th, 3i Atlas began a series of course adjustments, tiny, precise accelerations documented by the Gaia mission and NASA's Deep Space Network. Those corrections just happened to occur during the scheduled recalibration window for several key telescope networks, meaning that every adjustment was measured with newly tuned instruments, capturing the changes with maximum accuracy. In other words, we didn't just detect the object, we saw it at its clearest, in perfect alignment during our highest sensitivity windows multiple times. This doesn't happen with natural objects. Asteroids and comets come when they come. Their trajectories don't account for our calendar or our instruments. They don't wait for us to be watching, but 3i Atlas did. Or rather, it didn't avoid us. It moved into view, repeatedly, at moments of peak visibility. Not to hide, but to be measured, to be seen, to be logged, analysed, recorded. This has led some theorists to propose something bold, that 3i Atlas's timing is not passive. It is part of a sequence, a reveal, perhaps even a test of our observational readiness, not an accident but a checklist. Step 1. Approach during low solar interference. Step 2. Trigger emissions during network-wide coverage. Step 3. Align near Earth during instrument upgrade cycles. And maybe, Step 4. Wait. Because the biggest coincidence of all might still be coming. December 19th. That's when 3i Atlas will reach its closest point to Earth's orbital plane. During full system uptime across every major observation platform on Geo, the planet. It's almost like we're meant to see what happens. The only question is, what will we see? When 3i Atlas began accelerating after perihelion, scientists were prepared to explain it through standard cometary behaviour. Thermal outgassing, solar radiation pressure, or perhaps dust recoil. But as the data rolled in, it became clear this wasn't a simple boost. It was a pattern. The object wasn't accelerating randomly, it was accelerating rhythmically. From early November onward, observatories around the world began to record a strange cadence in the way 3i Atlas moved. Instead of a single velocity spike or chaotic bursts of motion, the object underwent a series of micro-accelerations, each spaced apart by nearly identical intervals. Specifically, every 5.26 days, a new pulse. This wasn't speculation. It was confirmed by datasets from the Gaia mission, the Deep Space Network, and radar measurements from the Goldstone Observatory. These micro-accelerations were subtle, fractions of a meter per second, but consistent. They appeared as brief surges in velocity followed by steady drift, then another identical surge, repeating with remarkable precision. To put it plainly, 3i Atlas was moving to a beat. Natural outgassing, the usual explanation for such motion, is inherently chaotic. It depends on heat exposure, surface composition, and rotational irregularities. But the rhythm detected here had none of that randomness. It was too clean, too punctual, too deliberate. Even more unsettling, the magnitude of each pulse was decreasing. The first 3 pulses after perihelion showed a clear logarithmic decay pattern, each one about 12% weaker than the one before. That's not only measurable, it's engineerable. It's exactly what one would expect from a controlled burn sequence, where an object initiates short propulsion bursts while preserving fuel or reacting to mass depletion. This type of profile is common in ion drives used on Earth-built spacecraft. These engines apply low-thrust propulsion over long periods, allowing for fine-tuned navigation with minimal force. If that sounds familiar, it should, because what 3i Atlas was doing looked exactly like that. The question, of course, is why? Why would a so-called natural object, an interstellar comet, initiate a sequence of perfectly spaced diminishing thrust events after its closest approach to the Sun? What was the purpose? One possibility is that these pulses served as a navigation correction routine, an effort to stabilize trajectory after perihelion and align the object with a specific future location. Analysis from orbital mechanics teams suggests that the rhythm of acceleration brought 3I Atlas into a cleaner arc, not toward interstellar escape, but toward the ecliptic plane near Earth's orbit, timed to arrive in mid-December. Another theory points toward communications timing. The third pulse, recorded on November 15th, coincided exactly with a detectable, low-band radio anomaly at 1.44 GHz, lasting just under 3 minutes. While the signal was weak and unconfirmed, its timestamp overlaps perfectly with the peak of the velocity surge. That's the kind of synchronization you'd expect between a maneuver and a transmission. Either way, the implications are the same. This isn't just about movement, it's about control. These rhythmic accelerations suggest a system that is measuring time, managing thrust, optimizing trajectory, and possibly coordinating emissions. No known natural process behaves this way. Not even solar sail models, driven by photon pressure, can account for the timing and decay pattern observed. They lack the regular interval and precise decay curve that 3I Atlas demonstrated. So what does that leave us with? Either we've discovered a comet that redefines physics, or we're watching an autonomous propulsion system in operation. A system that accelerates not because it must, but because it's designed to. And if it's following a rhythm, then it's following a schedule, a countdown, or a path that leads to something timed down to the minute. Because the next pulse is expected on December 15th. Just 4 days before 3I Atlas crosses Earth's orbital plane. We may not know what it's aiming for, but we know when. When studying distant objects like comets or interstellar travelers, space telescopes get most of the attention. Their clarity, isolation from atmospheric interference, and deep space optics make them ideal for high-resolution imaging. But in the case of 3I Atlas, some of the most critical and revealing data came from Earth itself, not from orbit, not from Lagrange points, but from the ground. Beginning in late October, as 3I Atlas approached perihelion, a network of ground-based telescopes, spanning observatories from Hawaii to Chile to the Canary Islands, was activated to track the object. What they recorded wasn't just brightness, it was feedback. Let's unpack that. The Las Cumbres Observatory Global Telescope Network, LCOGT, known for its worldwide distribution of synchronized instruments, began capturing time-lapse photometry on October 27th. As 3I Atlas moved into solar proximity, its light curve behaved erratically. Not noisy, not fading, but pulsing. Every few hours, the brightness of the object would spike by a few tenths of a magnitude, then drop, then spike again. This wasn't due to rotation. The rotation period of the object had already been estimated at over 16 hours, far too long to explain these rapid fluctuations. Instead, it looked like optical modulation. Now, under normal circumstances, brightness fluctuations can result from a tumbling nucleus reflecting sunlight from different surfaces. But the rhythm and symmetry of these pulses didn't match any known tumbling behavior. More importantly, they were coherent across multiple locations. The Subaru telescope in Hawaii, the Very Large Telescope in Chile, and a mid-size facility in Namibia all recorded the exact same brightness patterns, at the same times, across vast distances and different atmospheric conditions. That shouldn't be possible, unless the object itself is emitting or redirecting light in a controlled way. But the story gets stranger. Spectrographs attached to optical scopes in the La Silla Observatory recorded unusual absorption bands, patterns that shifted every time the object brightened. These changes occurred in the blue and ultraviolet ranges, suggesting not just reflection, but active interaction with solar radiation. Some researchers proposed that 3I Atlas might have variable albedo surfaces, patches that reflect differently depending on angle. But the coordination required to produce identical results across observatories ruled that out. Then came the interference readings. At the Mount John Observatory in New Zealand, an instrument used for high-frequency stellar spectroscopy picked up strange sideband interference during exposures of 3I Atlas. These bands, subtle but detectable, suggested an active modulation source, as if the object were creating weak optical signatures timed to specific intervals. The idea of optical modulation from a comet is unheard of, but for engineered systems it's routine. Satellites and probes use light-based signals to test alignment, initiate contact, or confirm receipt. In the case of 3i Atlas, what ground-based telescopes may have detected was a kind of feedback loop, not in radio, but in visible light. That possibility led several observatories to rerun their imaging data, using Fourier transforms, searching for encoded patterns within the flicker. Some teams claim to have found repeating sequences, others urge caution, but the timing aligns too closely with the known micro-acceleration pulses to dismiss. And then there's the biggest clue. It stopped. On November 24th, the pulsing light behavior suddenly ceased. The object stabilized. No more brightness surges, no more flickering, just steady magnitude. That date, not coincidentally, also marked the last planned calibration run of the European Space Agency's tracking schedule for December flyby targets. It's as if the object was saying, "You've had your window, now watch." Ground-based telescopes, limited as they are by clouds and night cycles, aren't supposed to capture this level of coordination. But somehow 3i Atlas lined up its behavior for maximum visibility during their peak readiness periods. That's not randomness, that's not luck, that's feedback, visible, timed, and possibly intentional. The James Webb Space Telescope was designed to look deep into the oldest galaxies, the coldest exoplanets, and the most subtle heat signatures in the universe. But when it turned its gold-plated mirrors toward 3i Atlas, the data it returned wasn't ancient, it was unsettling. Infrared imaging is more than just pretty pictures. It reveals heat, composition, and structural behavior that optical instruments can't detect. And because James Webb operates beyond Earth's atmosphere, at the Earth-Sun L2 point, it has an uninterrupted view, unaffected by weather or daylight cycles. When the telescope was scheduled to observe 3i Atlas in early November, astronomers expected the usual: thermal decay from solar heating, perhaps some patchy sublimation, maybe a few faint molecular emission lines. What they saw didn't match any of those expectations. The first anomaly came in the temperature gradient. Natural comets heat unevenly. As they rotate, their sun-facing sides grow warmer, while the far side cools rapidly. This creates a familiar thermal map: one hot hemisphere, one cold. But 3i Atlas displayed a uniform warmth across its entire surface, even on regions that should have been shielded from solar radiation. That's impossible without internal heat redistribution, and comets don't have that. They don't conduct heat well, they don't circulate it, but engineered objects do, via active thermal regulation. In spacecraft, this is done using heat pipes, phase change materials, or controlled surface coatings. The second anomaly came from the infrared emissions themselves. At the 10-micron band, James Webb detected a series of narrowband spikes, localized hotspots that pulsed at semi-regular intervals. These weren't natural outgassing events. They didn't appear in the surrounding coma. They were localized to the body itself, and most disturbingly, they followed a familiar cadence, approximately every 5.2 days, aligning with the known micro-acceleration schedule detected by Gaia. In other words, every time 3i Atlas surged forward, it also lit up in infrared. Not randomly, not reactively, but in sync. This thermal signature suggests something more than just heat. It suggests exhaust. Propulsion systems, especially low-thrust designs like ion drives, emit trace infrared signatures in narrow, short-lived bursts, and the shape, temperature, and decay curve of the emissions seen by Webb matched that model more closely than cometary activity ever could. Third came the composition scan. James Webb used its near-infrared spectrograph, NIR-SPEC, to break down the molecular contents of the object's surrounding haze. What it found was bizarre. High concentrations of ionized carbon monoxide, trace levels of sulfur dioxide, and unexpected metal-organic compounds that didn't belong in a typical comet tail. These compounds fluoresce in a unique way, particularly under solar UV radiation, making them ideal for optical signaling or plasma interaction. In short, they're useful in materials designed to be seen or tracked in the vacuum of space. Again, this is the kind of material you'd expect on a spacecraft skin, not a tumbling chunk of ice from deep space. Then came the final piece of data. On November 23rd, during a scheduled infrared sweep, James Webb captured what appeared to be a shadowed structure, a repeating void, pattern in the heat profile rotating slowly, vanishing and reappearing every few minutes. The model? A trilobal geometry, possibly symmetrical. Naturally, this caused immediate skepticism. Webb is precise, but not immune to artifacts. Yet the same thermal shadow was recorded again on November 26th, from a different position, under different light conditions. 2 distinct passes, same shape, same temperature dip. It's too early to call it definitive. But to those tracking 3I Atlas, it's one more hint in a growing pattern. This object isn't shedding heat like a comet. It's managing heat like a vessel. It isn't leaking gas like an ancient rock. It's emitting, rotating, cooling, and signaling. Whatever 3I Atlas is, it reflects sunlight by day. But it tells the truth, in the dark. In an era of real-time data, space agencies are rarely quiet, especially when an object from outside the solar system behaves unpredictably. Public updates, open-access datasets, and press releases are standard protocol. Transparency builds trust, and discovery is meant to be shared. But when it comes to 3I Atlas, the silence is louder than the data. From the moment 3I Atlas reached perihelion and began exhibiting unexpected behavior, public engagement from major institutions, NASA, ESA, JAXA, CNSA, fell to a whisper. Reports that would typically flow freely became sparse, delayed, or oddly incomplete. It began subtly. Initial perihelion data from SOHO and Parker Solar Probe were expected to be released by November 3rd, according to standard mission cadence. Instead, the uploads were pushed back without explanation. The public-facing HelioViewer portal showed gaps, entire frames missing. When researchers inquired, they were met with vague references to signal noise, processing delays, or routine calibration. Then came the contradictions. On November 6th, the official NASA Near-Earth Object Tracking page showed a projected deflection in 3I Atlas's course, marked as under review. Within 48 hours, that note disappeared. No explanation, no correction, just vanished. The trajectory reverted to the previous model, even as ground-based observatories confirmed a measurable shift in acceleration. It wasn't just a mission, it was rollback. European Space Agency staff who spoke under condition of anonymity noted that internal discussions had flagged 3I Atlas as anomalous as early as October 29th. Yet no public mention of this designation appeared in the ESA Science and Exploration Bulletin, a publication typically eager to highlight interstellar events. What replaced it? Silence. As public interest in 3I Atlas grew, spurred on by independent astronomers sharing data on social media, official sources began tightening. The Jet Propulsion Laboratory, which usually maintains active feeds and commentary on all tracked objects, issued no official blog posts or releases about the object after October 31st. Meanwhile, James Webb's infrared observations, some of the most revealing data to date, were logged under a generic identifier, not the usual catalogue ID associated with active interstellar targets. Even the public data archive masked the observational window under a cryptic tag. Extended Cometry Monitoring Program. Why obscure it? Some suggest internal debate, others suspect quiet concern. Because the agencies are watching, they're just not talking. Internal telemetry timestamps confirm that NASA's Deep Space Network continues to receive and process signal ecodata from 3I Atlas, meaning radar and communication systems are live. The Goldstone, Canberra and Madrid nodes have all logged contact points, but nothing from those logs has been officially released. FOIA, Freedom of Information Act requests are being processed, but responses are delayed, citing mission coordination with international partners. Even more telling is the behavior of military-affiliated systems. NORAD, which tracks not just satellites but deep space objects, has flagged 3I Atlas's December position as a temporary exclusion zone for certain classified launch paths. Again, no explanation. Just a reshuffling of flight corridors, and when private researchers reached out for clarification, no response. This isn't standard protocol, this is containment. We don't know what these agencies believe, but we know what they don't believe. They don't believe this is a typical comet, they don't believe it's inert, and most of all, they don't believe it's irrelevant. Because when major scientific institutions are silent, it's not because they have nothing to say. It's because they have something they can't say yet, or something they're waiting to confirm. And with December 19th approaching, the silence is starting to sound like preparation. They've run the simulations, they've seen the data, they know what it looks like, What they're not telling us is what they see coming. On the surface, December 19th appears unremarkable. It's just another day on the calendar, days before the solstice, weeks before year's end. No known meteor showers, no major solar events, no spacecraft launches. But for those tracking 3i Atlas, December 19th marks something far more precise, and possibly far more deliberate. That's the date when 3i Atlas is projected to reach its closest intersection with Earth's orbital plane, a near-perfect alignment not with the planet itself, but with the invisible disk we travel through each year around the Sun. This isn't a physical flyby, it's a dimensional crossing in terms of celestial geometry, and that matters more than most people realize. To understand the significance, we need to look at how space agencies track potential hazards. When assessing interstellar objects, scientists don't just calculate proximity to Earth. They measure how close an object will come to the ecliptic, the plane along which Earth, Mars, Venus, and nearly every other planet travels. When an object aligns with the ecliptic, it means one thing: interaction is possible. Gravity assist? Possible. Electromagnetic influence? Possible. Even observational optimization? Perfect. And that's exactly what happens on December 19th. According to data from the Minor Planet Center, 3i Atlas will cross the ecliptic within less than 0.02 astronomical units, a margin so tight that it triggers automatic alerts in deep space tracking systems. The intersection angle is 1.7 degrees, and the relative velocity is modestly low, just over 48 kilometers per second. That velocity matters, because unlike other interstellar objects like Oumuamua, which passed through the solar system on a steep arc and exited quickly, 3i Atlas has shown a tendency to linger. Its speed dropped slightly after perihelion, a deceleration not fully explained by any known forces, and it now moves in parallel drift with the inner solar system. This means that on December 19th, 3i Atlas won't just fly past a fixed location in space. It will match Earth's orbital rhythm, if only for a moment. Think of it as two runners on a track. Most pass each other quickly, but this time one runner slows just enough to run shoulder to shoulder. That moment of synchronized motion creates a window for observation, for interaction, or perhaps for something else. Compounding the mystery is the optical silence predicted just before the event. From December 17th to December 19th, 3i Atlas will pass through a region of space that's unusually devoid of solar reflection. Astronomers call this an optical shadow, a patch where incoming sunlight is partially obstructed by interplanetary dust, reducing reflectivity. That means any artificial emissions, infrared, radio or otherwise, would stand out more starkly. If there was ever a time for 3i Atlas to transmit, to signal or to activate, that would be the moment when all natural light sources fade, and only the object's own behavior remains. But there's more. Several observatories have pre-scheduled blackout periods for the night of December 19th. Public calendars from facilities in Australia, Chile and Spain show oddly timed technical maintenance blocks, despite December typically being one of the most active observing seasons of the year. It's hard not to ask, are they preparing for something? Even the James Webb Space Telescope has a narrow silence window from December 18th to 20, listed cryptically as Deep Field Orientation Adjustment. No specifics, no region of focus, all while 3i Atlas approaches its most synchronous point with Earth. If this were a random alignment, the timing wouldn't matter. But when an object has already shown engineered acceleration rhythms, directional thrust light and heat, emission cycles, coordinated visibility events, then a date like December 19th becomes something else entirely. It becomes a check-in point, a test of timing, maybe even an arrival. And if it's coming into phase with Earth, not to collide but to observe, align, or interact, then everything we've seen so far could have been leading up to this, not a warning, but a signal. In isolation, any anomaly can be dismissed. A strange trajectory, an unexpected pulse, a peculiar emission, each might have a natural explanation. But when similar anomalies repeat across multiple interstellar objects with eerily parallel behavior, it becomes a pattern. And now, with the strange behavior of 3i Atlas unfolding before us, many astronomers are revisiting two earlier cases that, until recently, were treated as unconnected curiosities: Oumuamua in 2017 and 2I Borisov in 2019. At first glance, all three are different. Oumuamua was fast and featureless. It showed no coma, no dust trail, and no obvious outgassing. It tumbled erratically and accelerated in a way we still can't explain. Borisov, by contrast, looked like a textbook comet, outgassing, glowing, shedding debris, except its velocity and chemical profile made no sense. Its carbon-to-oxygen ratio was unlike anything in the known solar system. And now 3I Atlas arrives, a hybrid of both, part comet, part mystery, with light pulses, rhythmic acceleration, and spectral anomalies. But here's what ties them together. Each of them entered the solar system on a hyperbolic path, not looping in like asteroids but cutting through as though sent from afar. And more importantly, each one arrived exactly 2 years apart. Oumuamua, October 2017, Borisov, August 2019, the 3. Atlas, October 2021. And now, in 2025, Atlas behaves unlike any known comet, just as its predecessors did. What's the likelihood that 3 separate interstellar objects, all with deeply unusual characteristics, would arrive in such a sequence? Statistically, negligible. Dynamically, improbable. But narratively, it starts to look intentional. Let's go deeper. Each object also revealed itself in stages. Oumuamua appeared inert, until it accelerated in a non-gravitational way after perihelion. Borisov looked natural, until spectroscopy showed its chemistry was alien. 3I Atlas followed the cometary playbook, until it began moving, signalling and timing itself with shocking precision. They don't behave the same, they evolve, as if each one is part of a learning system or even a probing sequence. It's like watching 3 different spacecraft with 3 different purposes, one to test our awareness, one to measure our instruments, and one to engage at close range. Oumuamua moved fast, too fast to study, but fast enough to spark global interest. Borisov lingered, releasing data-rich clouds, giving scientists the chance to build profiles. 3I Atlas, in contrast, is timing itself with Earth's orbit, matching our pace, delivering structured emissions, and perhaps waiting for something. If this were a coordinated sequence, what would its purpose be? That's the question now haunting segments of the astrophysics community. Could these 3 objects be scouts, signal relays, probes designed to observe how we observe them? Or even more provocatively, could they be a calibration sequence? Imagine sending multiple artifacts into a distant star system, not to contact, not to land, but to test its civilizations. Do they notice sudden objects? Can they detect chemical anomalies? Will they respond to acceleration pulses or radio signals? Do they coordinate globally? In other words, are they ready? Each of these visitors, Oumuamua, Borisov, and now 3I Atlas, left behind questions with no clear answers, but in their differences lies their connection. Because now we're seeing the 3rd iteration of the pattern, the most complex one yet, the one that doesn't just pass by, but stays, adjusts, and waits. And as 3I Atlas aligns with Earth's orbital plane on December 19th, the question becomes unavoidable. What if we were never meant to understand each object in isolation? What if the real message only emerges when we zoom out and view them together? 3 objects, 3 phases, 1 trajectory. Maybe they were never just visitors. Maybe they were the first question in a dialogue we haven't yet begun.